I would like to welcome you to the second seminar of the Long Road Ahead the Research Seminar Series. Today we have with us Professor Kourosh Khoshelham from the University of Melbourne. We're going to introduce him very soon. But meanwhile, I would like to say I'm very happy that he's with us in person, and one of the goals of this seminar is also to restart having face-to-face activities, and also, of course, with hybrid modality. So I also want to welcome whoever is attending remotely. Before we begin, I would like to show our respects to the Ngunnawal peoples that we acknowledge as the traditional guardians of the land on which this campus is located. And I would like to remember that this series is sponsored by the recently established AI Institute of UNSW and is part of the activities organized by the AI Hub of UNSW Canberra. Today, I'm very happy to welcome Professor Matt Garrett, who is the Deputy Director of the AI Institute of UNSW, and also the coordinator of the AI Hub of UNSW Canberra, and he's going to introduce our guest speaker. Thank you, Matt.
Thanks, Max. So this is actually the second Long Road Ahead seminar that Max and his team have organized on autonomous vehicles. It's a really important topic. Fully autonomous cars promise one day to really transform our lives. And it's going to make travel safer, less demanding. It means people can have mobility that previously couldn't have it. But it's a really difficult challenge for our age, because as well as all the technological implications of that and challenges that are there, which Professor Kourosh is going to talk about, there's all the ethical issues as well. So what's the effect of the workforce when we have vehicles being driven by machines instead of people? What's implications for ethics when there's a crash or something? Who gets the blame? Legal issues. So there's a lot of different issues across many different disciplines that have to be considered. So in terms of the seminar series in general, really grateful for Max and his team for organizing this. Also like to mention the other team members, Malad, Essam, Debbie, Helen Dickinson, Stephen Coleman, and Alexandra Malloy. They're also part of Max's team. And really grateful for the funding from the faculty to make this event possible. So just a quick word about the Institute. So across UNSW, there's something like about 300 different researchers that are involved in AI, machine learning, data science in some way. So we do have quite a large critical mass in this area, but we're quite new. That the Institute was only opened in September this year with its formal opening. So we are a very new thing, but activities like this are trying to increase collaboration and get people to know about each other's research so that we can all start working together and break those silos. Anyway, apart from that, I just want to thank Ken Steer and the folks at ICTS for technology, and Charlie Jin at the AI Institute for helping out with getting this online through Zoom. And without further ado, I'll introduce the speaker. So Kourosh is a professor of computer science in spatial information at the University of Melbourne. He received his PhD in geoinformatics from Hong Kong Polytechnic University in 2004 and held assistant professor positions at Delft and the University of Twente before joining the University of Melbourne in 2015. He's co-authored over 170 referee publications on topics related to spatial information and 3D computer vision. And his research interests include autonomous mapping, positioning and navigation, augmented reality, and development of machine learning methods for automated interpretation of imagery and point clouds. Kourosh is the recipient of several prestigious awards, including the President's Honorary Citation for Special Personal and Meritorious Contributions to the International Society for Photogrammetry and Remote Sensing. So thank you very much, Kourosh, for coming. Really appreciate you making the journey, and best of luck with the technology today.
To acknowledge the traditional owners of the land on which this seminar takes place and pay my respect to the elders past, present, and future. And thank you for organizing this seminar, inviting me. I think it's a great opportunity to discuss autonomous vehicles as an interesting development in our era. And I'm very keen to have a conversation that's a little bit broader than my interest in the computer vision aspect, as Matt mentioned. I'm sure there are other dimensions, including the ethics, the regulations, infrastructure, which are equally interesting. And I'm very keen to have this conversation with you and learn more about these new dimensions. So just to check audience online, can you see my slides? All good? All right. No. Okay. So I thought I'll talk about the autonomous driving in general. I'm sure you're familiar with the autonomous driving, but one of the key requirements of autonomous vehicle is the driving scene understanding or perceiving the road environment. And I will focus on state of the art in driving scene recognition and understanding. I will talk about the main approach to driving scene understanding, which is machine learning. And again, I'm sure you're familiar with machine learning. And then we talk about the challenges, which I think is the more interesting part of the seminar today. I will look at these challenges from the computer vision perspective, from the perspective of understanding the road environment to enable autonomous driving, but I'm also interested in learning your perspectives about the challenges from other dimensions, including regulation, policy, infrastructure, and ethics of autonomous vehicles. All right, so why do we need autonomous vehicles, or do we need autonomous vehicles? I think that's a question that there's debates, but in my perspective, the main benefit of autonomous vehicles is the safety of road environments. We know that most of the road accidents are caused by human error. The driver can be drunk, sleepy, they don't pay attention to the road, and that causes driving the road accidents and crashes. Autonomous vehicles don't have that problem. They never get drowsy or drunk, and they always pay attention to the road. So in that sense, an autonomous vehicle can be a safer driver, and therefore safety is the paramount benefit of autonomous vehicles. So when with autonomous vehicles, we can avoid driving accidents, road crashes. That means there's also less congestion in roads. Most of the congestions are caused by traffic accidents. So there's going to be improved traffic flow. Autonomous vehicles also provide mobility options for disabled people, elderly, and people who have special needs and cannot drive for any reason. Now, I think it's important to set the scene when we say autonomous driving, what actually we mean by autonomous driving. And especially I know because I will be challenged by the ethics of autonomous driving. I think it's important to understand the different levels of automation in driving. What you see on the slides, I think this is commonly accepted by the SAE organization. If I could get rid of this. Does it stop the recording if I do? No, I think it's just, yep. So SAE defines 5 levels of automation in driving. Level 0 obviously is manual driving, where the human is completely in charge of the vehicle. Level 1 is when the vehicle can do one task automatically. And one example is the cruise control. You put your vehicle on a cruise control, constant speed, and it can maintain that speed. And then you can just, lift your foot from the gas pedal. Level 2 is when the vehicle can perform several tasks automatically. Again, what good example is the adaptive cruise control, where the vehicle can brake automatically when there is an obstacle in front of it, and can accelerate when there is open road and maintain a certain speed. Or it can do lane keeping, stay within the lanes. Level 3 is when the vehicle can perform all driving tasks automatically under the human supervision. So the driver is still in charge, the human driver is in charge of the vehicle, but the vehicle can self-drive in principle. Level 4 is one level higher, when the vehicle can do all driving tasks, even without the human supervisor, in certain conditions. If you have a mapped environment and you know where everything is, and in favorable weather and lighting conditions. And then level 5, which is the highest level of automation, or full automation, is when the vehicle can self-drive under all conditions, and the human driver cannot even override the autonomous vehicle. So the vehicle is in charge of driving. Now, what's important to understand is that at the moment, we are working towards level 3 automation, which means the vehicle can self-drive under the human supervision. So the human driver is still in charge of the vehicle, but the vehicle can do all the driving tasks. And level 4 and 5 are for further future, if it happens. So I'm a bit pessimistic, but probably automotive engineers are more optimistic. But at the moment, we talk about level 3. Even when you see, for example, Tesla advertises their driving automation software as full self-driving software, it's not really, it's actually quite misleading, because it's not full self-driving in the sense of level 5. It's still level 3 and requires the human driver to be in charge of the vehicle. So this is where we are currently. Now, even for level 3, which is the vehicle can drive automatically under human supervision, that autonomous vehicle needs a certain capabilities to be able to self-drive. Now, I look at these requirements from the perspective of the perception requirements. There's, of course, control, mechanics, and all sorts of other things for a vehicle to be able to drive. I will only focus on perception requirements. The vehicle should be able to detect the road boundaries and the lanes. That's the first requirement, because you want to drive on the road. Second requirement is to be able to recognize traffic signs, because you want to know what's the speed limit on this road, for example, where you can stop and where you can't stop. You need to be able to recognize traffic participants, other vehicles on the road, pedestrians, bicycles, motorcycles, and so on. There might be road incidents, which are not happening very often, but they might happen. The vehicle should be able to detect road incidents and make a decision whether the road is drivable or whether the vehicle needs to reroute and take an alternative route. And last but not least, the vehicle needs to be able to localize itself. It needs to know where it is before it can decide how to get to the destination. So navigation is a requirement, and for that navigation to happen, we need accurate localization. The vehicle should know where it is. This is an example of, this is actually Waymo dataset. Google Waymo has released this dataset, and you can see what an ideal autonomous vehicle should be able to do. It should be able to recognize pedestrians, cars, anything that's moving on the road environment, but also the static objects in the road environment, including the road itself and all the infrastructure around the road. Okay, so how do we achieve this goal and how do we satisfy these requirements? Driving scene perception is essentially a computer vision task. We want the computer to be able to look at the road environment and understand the road environment, and then that would enable self-driving. This requires first sensing the road environment, for which we use sensors on board the vehicle. And then when you capture data by the sensors, then you need to be able to interpret those data automatically to understand what's around the vehicle. The sensors that are very commonly used nowadays on autonomous vehicles are cameras, LiDAR sensors, and radar. There are a few other sensors, but they're not used for perception. There's, for example, ultrasonic sensors used for parking. You know, when you want to park and the car beeps when you're too close to the obstacle, that's the ultrasound working. But it's not used for perception. For understanding the road environment, these are the three main sensors that are commonly used. I just learned today that even Tesla is a non-believer in LiDAR. They only use camera, but I learned that they also planning to rule out radar from their sensors on board their vehicle. So they only rely on camera. But this example that you see on this slide is the Uber car. And you can see it has a suite of different sensors. And most of the other car manufacturers are similar. They use a data fusion approach, which means they rely on multiple sensors instead of just one. So usually there is the camera and LiDAR, which is a laser sensor and can measure distance by sending laser light, and then radar. And the perception happens by fusing data captured by all the three sensors. Now, the processing of that data is usually done by the machine learning approach. You're probably familiar with machine learning, but it's basically learning by examples. There are different types of machine learning methods. The one that's very commonly used nowadays is supervised machine learning, where you show some examples to the computer, and the computer learns from those examples. For example, you show an image of a pedestrian, and not one image of a pedestrian, but many images of pedestrians, and the computer learns what pedestrians look like. And then when it captures an image, it can detect and recognize pedestrians in it. So this machine learning approach, or to be more specific, supervised machine learning is basically a two-phase process. We start with a training phase, which you see on the left side of the screen. In the training phase, basically you have those examples, and we use basically a network that can extract features from those examples, prominent features of the objects or entities that you're interested in. So this is the feature learning network. What it basically does that it compresses your data into a very compact feature vector. And that feature vector is then, this is the feature vector is then fed into another part of the machine learning model, which is either a classification layer or regression layer. and then the output is a prediction. So during the training phase, we look at these predictions by this network and compare that with the predictions that are part of our example. So we show, for example, an image of a pedestrian. So that's the prediction is that it's a pedestrian. And then the network will learn to make predictions that are consistent with the examples that we show to the network. So this is the training phase. During the training phase, basically an optimization problem is solved. We basically determine the parameters of these networks so that the network can predict according to those examples that we show it. Once the model is trained, then there's the inference phase. And that's basically when you deploy your machine learning model to the open world. You go to basically with your car driving on the road, and then your sensors capture data, images, LiDAR point clouds, or radar images. And then we use the trained network. So the network that we have already trained in the previous phase is used here to extract features from your data. That means compresses your data into a compact vector of prominent features of the objects or entities you're interested in. And then you have the classification or regression layer, which performs the prediction. And then that prediction is the basis for autonomous driving. For example, recognizing the road, recognizing traffic participants, or estimating the location of the vehicle, which is a regression task. So I talked about the requirements or the different tasks of autonomous vehicles in perceiving the road environment. I thought I'd give you an overview of the state of the art and what's happening at the moment in research. And then we talk about the open challenges, so the problems that are still unsolved. So to start, let's look at the detection of road boundaries and lane markings. Where are we currently? Can the autonomous vehicles detect the road and the lanes at this moment? So the typical approach to road recognition and lane recognition is data fusion, usually camera and LiDAR data combined together. And then there is the approach is the machine learning approach. So again, a model similar to the one that you see here. Basically a machine learning model, the inputs are images captured by the camera and point clouds captured by the LiDAR sensor. So the LiDAR captures point measurements where each point has a 3D coordinate, and then the output is a 3D point cloud that represents the geometry of the environment. And then this network will basically learn to detect the road boundaries from both image inputs and also detect lane markings. So this is the common approach. And in some of the recent works, they also use existing maps, for example, open street maps, especially when you want to drive on a road that's not properly marked or weakly marked, or sometimes there's no marking. You know, if you drive in a rural area, it's hard to detect the road boundaries and the lanes. The lanes might not even exist. So for those situations, using a map is essential, as we will see later. I'll talk about the maps in a minute. So this is an overview of what currently we can do for recognizing roads. This is from the Coyote Benchmark. Coyote is basically a benchmark that was designed to compare the different methods that were developed for driving scene perception. So if you look at the road estimation part of Coyote, for urban roads where the roads are marked properly. If you look at the benchmark, you see this is the first one, the top one, or the best performing method. It achieves a very good precision score, basically F score of 97%. So that means if you think of the road surface, it can recognize the road surface 97.5 or 97.05 of the area of the road surface, which is pretty good. So that means the current methods can actually recognize the road environment and the boundaries quite well. But if you look at the urban roads that are unmarked, then you see the precisions are a little bit lower, but not much. So this is still 97.04. This is 97.05. It's actually quite close. Lower performance when it comes to lane estimation, even for marked roads, so 94.4%. But overall, if you look at the Coyote benchmark, and I've shown here only the top performing methods, in general, you can see all these methods work quite well for recognizing the road boundaries and lane markings if the road is properly marked. In other environments, in other roads, rural roads, it's usually essential to use an existing map. The other task that the autonomous vehicle should be able to do is traffic sign recognition. And traffic sign recognition is another example of the tasks that the computer can do pretty well. This is an example I've chosen from 2012. This is the German traffic sign recognition benchmark. And basically they created a data set of images of traffic signs, and they compared the human performance with the computer performance. And it's interesting that the computer outperforms the human. This is one of the maybe first examples where the computer machine learning approach could outperform human. So if you look at the results here, this is the correct classification rate. And you see the top one is the committee of CNN. It's basically a machine learning model that can recognize traffic signs with a precision of 99.4%, which is pretty good. And then human, the best individual human and the average of human is next. So I mean, if you look at the interface that they used for the human recognition of traffic signs in defense of the human, the images are actually quite small. Even though that the interface allows you to enhance the image and enlarge it a little bit, but it's actually quite hard for some of these traffic signs. So it's interesting, in their paper, they talk about also the situations where the human participants could not recognize the traffic sign correctly, and situations where the computer could not recognize. And it's interesting that the ones the computer could not recognize are mostly where the traffic signs are overexposed or completely, white, if there's nothing really to see. Whereas the ones that human makes mistake, the traffic sign is still visible, but it's not easily recognizable. So I think this one also is one of the tasks that we can consider more or less solved, because computer actually performs quite well. It can recognize all the traffic signs in specific conditions, of course. We should not forget that these are when you have good images, your camera works. That means sunny days with good weather, perfect conditions. If you drive at night or poor weather conditions, then it's a completely different story. But we're talking about level 3, which means driving in good conditions under a human supervisor. The next task is recognizing traffic participants. And this one is a little bit more challenging because the traffic participants are actually a very diverse group. You have pedestrians, other vehicles, bicycles, motorcycles, but a lot of other objects that might be on the road surface, obstacles. And for the autonomous vehicle to be able to self-drive, it should be able to recognize those objects, and that's the challenge. So this, for this task also, the fusion of camera and LiDAR is the most common. I've chosen another benchmark to look at the best performing methods. This is NewScenes, because NewScenes is one of the few datasets that has a higher variety of object types. Whereas, for example, Coyote that I showed earlier, it has only 4 types of objects, 4 or 5. But if you look at the top performing methods on NewScenes dataset, then you see they all use camera and LiDAR, fusion of both. Radar is also gaining traction. People are also interested in using radar as well. And then if you look at the average precision, you see it's about 75%. So the precisions are not as high as, for example, road boundary detection or lane detection because of the diversity of the objects on the road environment. This is an example one of our students has done by basically fusing imagery and LiDAR data tested on one of NewScenes scenes. And it's interesting because we learned how important LiDAR is for recognizing objects, because you might be driving at night or bad weather conditions, and your camera is basically useless. When there is heavy rain or snow or fog, you don't see anything in the camera, in the images. But LiDAR is influenced, but much less. So at night, there's no problem because LiDAR has its own laser light. It doesn't depend on ambient light. But in poor weather conditions, it also works, even though the data is a little bit noisy. It's interesting. Maybe I go back a little bit. You see objects on the side of the road that are recognized, but you don't really see anything, right? Because LiDAR here, it takes over. And when you fuse imagery and LiDAR data, even though there's not much light and your image is dark, still your LiDAR can pick up those objects on the side of the road, because the vehicle headlights basically show in front of the vehicle on the road surface. And you might have seen an accident where a bicycle just crashed to one of the Tesla or Uber cars, I think. It's because the car doesn't see the side of the road, only sees in front of it. The other task that is challenging, but is required for an autonomous vehicle, is detecting incidents, road incidents. Incidents are 2 types. One is signed. For example, there is a crash or a tree fallen on the road, but the relevant authority organization comes and puts signs around it, those traffic cones, for example, or a fence around it. So then there's a sign, and that one is quite easy to recognize because all the autonomous vehicle has to do is to recognize those signs, the cones or the whatever they put around it, fences around the objects. The challenging scenario is when the incident is unsigned, and most of the traffic incidents are unsigned, especially those that are ephemeral, the temporary ones. For example, a tree falls on the road, or there's a road collapse, there's an animal crossing the road. So these are incidents that are usually not signed. And then the vehicle should be able to recognize these It's important from two perspectives. One is the safety of the vehicle and the driver, because you don't want to crash. And the other one is by recognizing incidents. For example, if the road is blocked, you can reroute, but you can also inform other vehicles in the vicinity, given that future vehicles will be connected and they can communicate information between each other. So the first vehicle at the scene, if it can detect and recognize the incident, you can inform all the other vehicles and they can reroute, and that would help the traffic flow as well, make the travel time shorter. This can be done by vehicle-to-vehicle communication, but also vehicle-to-infrastructure communication. So in the future, we think there will be infrastructure around the road which can also send and receive signals and communicate with the vehicles. So then you can receive this information from the infrastructure around the road as well. The problem with detecting road incidents is training data. So remember, we said machine learning is our best approach to driving scene understanding. And machine learning requires examples, or which we call training data. And training data of road incidents is very hard to collect. Now, this is an example of a work we did with a master's student from the Netherlands and a colleague from the Netherlands. We collected data from the Google, Flickr, and another source, but only images. So of course, images are widely available, but of course you need to, annotate and label those images. You need to prepare your own training data. So you need to be able to recognize the incidents in the image and label those images. But LiDAR data, how often do you come across a vehicle that has a LiDAR and goes to witnesses a traffic incident? It's very rare, and data is usually not stored anywhere. So that's an issue. If you think that vehicles should use camera and LiDAR and maybe radar all together to understand the road environment, this is a challenge. We don't have the right data for recognizing traffic incidents. But if you have right data, so if you have the images and then the weather is good and it's nice daylight, then it works quite well. As you see here for these 8 categories of objects, accuracies are above 90%, some of them up to 98%. So it's pretty good. That means that the vehicle, the machine learning model, can recognize incidents if it has good data. But then again, in favorable weather and lighting conditions. Another interesting challenge for road incidents is that the vehicle needs to be able to assess the risk of the incident. And the risk is how likely is the incident, or how likely is the situation to lead to an incident. And if it happens, what is the impact? How serious is the incident? And that's an interesting, I think that's where we go to more towards the philosophy of a vehicle being able to really judge a situation that's not so easy, and it's actually quite a complex decision making here involved. I have some example again from this paper that we did a few years ago. So this one is a road with animals on the side of the road, but there is a fence. The fence is not very clearly visible, but there is a fence. So this is a situation where, as a human, when you look at it, then you say, okay, there's a fence between the animals and the road. So it's not very likely that sheep can, jump over the fence and come to the road. So the likeliness is low. And if you were driving on this road, you would just continue driving, right? But it's for the autonomous vehicle, this is a challenge because the fence is not very clearly visible, and recognizing the fence and also understanding that the sheep is on one side of the fence and the road is the other side, and the sheep cannot jump on the fence. All of those things, they are hard for computer, easy for human, hard for computer. The other case is a flooded road. So part of the road is flooded. What would you do in this situation? As a human driver, would you stop? Would you think that this is too much water? Or would you think I would just drive through it? So this is a situation where you need to assess the likelihood and the impact. So how likely is it to be a serious issue if I drive through it, and what's the impact of it? And again, this is a challenge for the autonomous vehicle to assess the risk. And the third example is, again, animals on the road. This time there's no fence. So this is the case where it is likely that the animal can cross the road, and therefore the vehicle should be able to make that decision that there's a high likelihood, but what's the impact if it happens? All right, the last task, which I think is very important for autonomous vehicles, is localization, or estimating the exact position of the vehicle on the road. And when I talk about this issue, most people remind me that we have GPS, GPS, when you look at your mobile phone and you know your position because satellites are always available. The problem is GPS or GNSS is not always available, especially in densely built up areas, urban areas. When you have tall buildings around you, if you drive through a tunnel, any indoor environment, indoor parking lots, your GPS is not working. So that means your vehicle will lose the location information. And therefore, we need another sensor to complement GPS and be able to estimate the position of the vehicle. So the current solutions are by combining visual sensors that are used for perceiving the road environment, use these for vehicle positioning, combine it with GNSS. Another issue with GNSS is that if you want to do accurate positioning, you need an infrastructure. So if you use your mobile phone, there's no infrastructure needed. I mean, the satellites are just orbiting the Earth, but that's there. But it gives you meter level accuracy, like 10 meters. That's not sufficient for autonomous vehicles, right? If you want to achieve high accuracy, and it's possible with GPS, you can do centimeter level accuracy. 5 centimeters, even 2 centimeters is possible. But it requires infrastructure. For example, base stations with GPS receivers around the road environment that send you correction signals. And that infrastructure is not easy. So we said challenges. One is infrastructure. You're talking about a whole country or the whole world, So establishing that infrastructure is not really practical. But other visual sensors, they eliminate the need for this infrastructure, especially if you use camera or LiDAR and then combine with GPS, you can do accurate positioning without the infrastructure. Now, how do we do positioning with other sensors other than GPS? Again, camera and LiDAR are the most commonly used. With camera, the problem is the method that is often used is visual odometry. And with visual odometry, you have the drift problem. You can do the same with LiDAR. Basically, you connect your a sequence of images or point clouds and estimate your trajectory. But because this is all relative to a previous position, then the errors accumulate and your trajectory drifts from the actual trajectory. So this is an example of a work we did with students a few years ago. And if I can move this here. So basically a spherical camera on top of the vehicle, mounted on top, because if you're driving in a dense urban environment, then you want to use the view of the side, the buildings, because they have a lot of texture and a lot of features that's suitable for positioning. And then by tracking these features in the image, you can basically do visual odometry and estimate your position. The purpose of this was mainly to understand how much drift can we expect, and is it too much or is it still within an acceptable range? For example, can I drive, say, 1 kilometer and still maintain a good positioning accuracy using visual odometry or not? So what we learned from this experiment was the drift was 0.3% of the trajectory length. So in 100 meters, 0.3 meters, 30 centimeters, only 100 meters. So it is significant. LiDAR is more accurate. You can do more accurate visual odometry, but you cannot eliminate the drift if you do odometry. You can eliminate the drift if you use SLAM. And SLAM includes loop closing. So basically, you connect your consecutive data, like point clouds with LiDAR, and you estimate your trajectory. And as soon as you make a loop, you come to a position you recognize you've been before, then you have an estimate, a new estimate and an old estimate of your position, and you can use the discrepancy and correct your whole trajectory. So this is called loop closing. A good example of loop closing is this work, OverlapNet. It's quite recent, from 2020. The problem is you cannot do loop closing for vehicle positioning and navigation because you're, you can't expect the driver to make a loop just to estimate its position. What if you want to just drive a straight road, So loop closing is not a practical solution. It's useful for mapping the road environment because SLAM is simultaneous localization and mapping. For mapping is fine, but localization needs to be real time. Delay is not really acceptable. So what do we do? How do we do positioning without drift using just a camera or a LiDAR or both? I think the solution is to use an existing map. And a map is useful not just for for positioning, for localizing the vehicle, but also for situations where your sensor data are not reliable. So if it's heavy rain or fog or snow or pitch black, then you can still use the map. So your sensors don't give you anything, but imagine that the traffic sign can send you the signal, whether it's a red light or green light, and you have also a map that shows where the traffic sign is. So you can use this information from the map when your sensors are not working. But also for localization. So if you can match your data that you capture with a map, an existing map, that gives you localization. So the solution that is very promising is by matching LiDAR data with HD maps. HD maps, high definition maps, are basically specialized maps that are, we think they will be necessary for autonomous driving. Basically 3D maps with all the road infrastructure, including traffic signs, traffic lights, and everything in it. So by matching your LiDAR scans with an existing map, you can estimate your position. And this is what you see here. There are methods that do this quite robustly. You can also combine this with your LiDAR odometry. So if you basically capture this sequence of LiDAR data, LiDAR point clouds, and if you match these, you estimate your position incrementally. And then if you match with the map, the existing map, you can eliminate the drift. So that's a very promising solution. We've done some work with PhD students in this area and integrated the solution that comes from LiDAR with GNSS. And I think this is basically a very promising solution because integration of GNSS and LiDAR improves the accuracy, improves the availability, because GNSS is not always available. Same for LiDAR. Maybe you're driving in an environment where the actual scene is different from your map. The map may not be up to date. You know, the road environment is very dynamic. It changes all the time. So what if there is a difference between your current scan and the map that you have in your system, right? So it might, your LiDAR-based positioning could also fail, just like GNSS, but they complement each other. And the fusion would make this positioning solution more available, which is very important. And it also eliminates the need for infrastructure. And I think this is even more important, because we've learned that if we use LiDAR odometry or LiDAR map matching and integrate it with GNSS, you can do accurate positioning without needing GNSS infrastructure like base stations. All right, I talked about HD maps. I think it's good to just mention what it is and some of the developments in HD maps, high definition maps. It's actually an old concept. And a HD map is a very detailed 3D map that we think autonomous vehicles will need. It's different from the navigation maps that you see in your navigation device in your vehicle today. And there are different layers in a HD map. There should be information about the road and road boundary and the lanes. There should be information about the landmarks, including traffic signs, traffic lights, but also like light poles and anything that's static in the road environment. But we don't, at the moment, we don't know what is the correct representation for HD map. I'm advocating voxel maps, but most of the vehicle manufacturers are going for vector maps, because vector maps are light, easy to download from a central database, but they are very hard to generate and very hard to update as well. Whereas voxel maps, they can be generated automatically and updated automatically. But it's good to mention also the first time that a vehicle drove automatically without a driver, when the driver was there but wasn't driving, using a HD map. That was in 2013 when Mercedes-Benz did a test drive. So they experimented with their intelligent drive, a long stretch of road, 103 kilometers in Germany, self-driving, but they had a very good map, very detailed map of that stretch of road that they used for their experiments. All right, so let's talk about some of the challenges, which I think they are interesting from the perception angle. And we talk about the other challenges from the ethical later. From the perception, I think one is the diversity of the road environment. Road environments are very diverse. There is diversity in terms of geographical locations, but also what you can expect to see in a road environment. So roads, for example, in Australia are quite different from roads in the US or in the Europe. So what happens to an autonomous vehicle when they drive in a new road in a different geographic location? Because remember, the intelligence in the autonomous vehicle is the machine learning model that's been trained using some examples. Those examples might be from, for example, US, and then you drive in Australia. What's going to happen? So the autonomous vehicle might see something new and should be able to recognize that something is new. I haven't seen the AI model should be able to say, okay, this is something new. I haven't seen this. Current models, they just misclassify. They say, okay, I've seen images of cats and dogs, and all types of objects on the road. First time they come across a kangaroo on the road, they say, ah, that's a cat or a dog. They just assign the wrong label because the current models, they don't know what is that something is new that they haven't seen. I'll talk about this a little bit more, but there's another challenge with the diversity of roads, diversity of geographic locations, and that's when you have the same objects that the model has seen, but those objects have different appearances. So your model has seen buildings and, you know, cars. Okay, cars look the same everywhere, but buildings look different, right? You know, your model is trained in an area with high-rise buildings. You drive an area with, you know, one-story buildings, villa houses, whatever. They look different. Trees look different. Vegetation looks different. Traffic participants might look different. If you drive in the Netherlands, you see a lot of bicycles. In Australia, you see very few. So these are the differences in appearance. Poor visibility condition is a challenge. Most of the methods that we see today, they are tested on data captured in good weather conditions, good lighting conditions, nice daylight, and, you know, sunny days. Scarcity of training data is another issue. We use machine learning. Machine learning needs examples. Collecting those examples is a problem. So I'll just give you some examples of these and what I think would be potential solution, but I'm open to, you know, discuss this further and see what you think, and also what are the other challenges from your perspective. So in terms of new objects, the problem is, if you think about the machine learning model, the problem is that most of these machine learning models are basically trained on a closed set of objects. So we say it's a closed set, for example, image classification or object recognition. What we need for autonomous vehicles is open set object recognition. That means that the model should be able to recognize things that it has seen before, and then anything else should be basically labeled as new. So in machine learning terminology, we call this out of distribution, because the model has learned a distribution of objects that it has seen, and then you see something that's new, that's out of distribution. Instead of wrongly classifying that, assigning the wrong label, you should say, this is out of distribution, this is out of my knowledge, it's new, please label this for me. So then this is where you should, the AI should refer to the human driver and say, okay, I see something new, can you please label for this for me? And this is called active learning in machine learning, when you learn by examples and you basically return those examples to the human experts to label these for you, and you learn from these. But usually in this, when you see something new, there's only one instance of that object. So the machine learning model should learn from that single example. And that's a challenge on its own merit. Single shot learning is still a problem. The other thing is you need to incrementally learn. So the AI model, the machine learning model, should learn from these new examples, but not forget the previous examples. And you can't say, okay, now I have a new example, let's just erase my machine learning model and do the training from scratch, again, using my new examples as well, right? This takes us too much time, and it's not practical. So you need to incrementally learn from new examples, keep your knowledge base, just expand it with new examples. And this is a challenge. There's a lot of research happening on this topic because there's the problem of forgetting your current examples when you see new examples. The issue with diversity of driving scenes, driving in new environments where you see the same object but different appearance. This is basically, I think the solution is using domain adaptation or scene adaptation. So you need to develop machine learning models that can adapt to new environments and the new appearance of the objects they have seen. The problem is, if you want to do this adaptation, usually you don't have many new examples. So you've trained your model with high-rise buildings. Now it can recognize all the buildings, high-rise buildings. But when you drive in an environment with single-story buildings, you usually don't have many examples. And ideally, you want your model to learn that these are still buildings, but in an unsupervised way. So without additional examples, because those examples are problematic. So this unsupervised scene adaptation is a new research direction here. Driving in poor visibility conditions, there is recently a lot of attention to this because especially in countries like Canada, for example, where driving in wintertime is really a challenge. So they're basically trying to create data sets that represent poor visibility conditions, bad weather conditions, nighttime conditions. One interesting question here is, should you train your AI model, your machine learning model, using all sorts of data, including good weather and bad weather, day and night? Should you train a generalist model, or should you train multiple specialist model? One specialist snow recognition model, one specialist rain model, one specialist fog model, because it's easier for the vehicle or for the AI to say it's day or night or sunny, rainy, and then use that specialized model for that condition. So recognizing that it's rainy, it's easier than recognizing objects in a rainy environment. That's what I'm trying to say. But that's a question that hasn't been answered yet. And some of my students are working on it, but we don't have a good answer for you yet. The scarcity of training data, that's another issue, because those examples that you need for your machine learning, they need to be labeled manually using human experts. That labeling is a tedious task, takes time. And sometimes it's not possible, like I mentioned, for incidents, LiDAR data of incidents. We don't really have data. So there is recently a lot of interest in using synthetic data for machine learning. And for driving scene understanding, there are two ways you can do this using synthetic data. One is using a synthetic environment. For example, Carla is an example of a synthetic environment. So basically have a 3D model of a city, and you can put a car and drive that car in that simulated environment, and you can capture data, images, LiDAR data, and then you train your model using synthetic data. The other approach is to generate synthetic examples. And this is a work I've done with some students recently, where you can develop generative machine learning models that look at real examples of, for example, cars or pedestrians, and they generate synthetic examples that look similar in terms of appearance to those real samples. And then you can augment your set of examples with the synthetic ones. So real examples and synthetic examples together lead to better performance for object recognition. All right, I think I've spoken more than I planned, but just to summarize, I think the tasks that I mentioned as requirements for autonomous vehicles, some of them are more mature than the others. Detection of road boundaries and lane markings, I think we can consider mostly solved nowadays, especially in good weather conditions and good lighting conditions. Current vehicles can also do this. Vehicles with adaptive cruise control, I've seen vehicles that have lane marking, it's quite reliable. If you have properly marked roads, the vehicle can actually keep within the lane, and that's we can assume that it's solved, unless you are driving in rural areas and the roads are not marked, there's no lane marking. And in those cases, it's still an issue. And you would probably need to use an existing map of the environment. Recognition of traffic signs. Current vehicles can do this quite well. As I said, the benchmark results also show very high performance, better than human, so that the computer can do this better than the human. So that's not an issue. But the other tasks are, I think there's a lot of there's a lot of research to be done to get there. One is the traffic sign, recognition of traffic participants, which is still a challenge. And if you look at the current methods, if you look at the benchmarks, public benchmarks, you see the performances are not very high, especially for objects that have a large diversity. For example, if I remember from New Zealand's truck or special vehicles, existing models have a very low performance because there are not many examples of those objects. Bicycles are a challenge because they appear in different ways, in data. Road incidents is very important and is still a challenge because we don't have good data. And vehicle localization, I think we have a long way to go to be able to accurately localize the vehicle using vision sensors. So some of the directions for future research, I think these are the ones that I'm interested in. I think they're very important. One is open set object recognition, where your model can recognize new objects and don't assign the wrong label to it, return it to the human for labeling, and then learn incrementally. So all of these together, I think they are important. Unsupervised scene adaptation. Most of the AI models, machine learning models, are trained on public data sets, and these are mostly from Europe and the US. So Coyote is from Germany. The other ones, most of them are from the US. So imagine that your machine learning model is trained on that data, and then you drive in Australian roads. Your model should be able to adapt to this new scenery of the roads in Australia. Single shot incremental learning, I think it's very important because you want your vehicle to continuously learn and expand its knowledge base without dropping in performance in scene recognition. And then using synthetic data, I think one very interesting direction here is domain adaptation. Domain adaptation is where you train your model on one domain, for example, to recognize images of cats, and then you apply it to another domain. So maybe the different types of cats or different views of cats. And between the synthetic and real data, there is this domain gap. They don't look the same. And then you need to fill in this gap. So you need models that do this domain adaptation from real to synthetic or from synthetic to real before you can use synthetic data. All right, that's it. I'll be happy to answer any questions you might have here and the audience online. Before I close, I would like to acknowledge contributions from students and colleagues. I've shown some of the results of the student projects. And yeah, that's it. I'm happy to answer any questions. Thank you.
Thank you. Or I can carry the microphone around.
Yeah, that's right.
For the presentation, I have two questions. First, for the navigation, for this application, what is the accuracy requirement for the location?
seen 10 centimeters is something that most people have learned. 10 centimeters. Just really make sure that people this length. Sorry.
Pardon me.
The online audience. So sorry, the question was, what is the accuracy requirement for vehicles? And my answer was there's no value that everybody agrees on, but what I've seen in the literature is 10 centimeters that is mentioned as the requirement. So because you want to know the vehicle is on this lane, not the other lane, and that's 10 centimeter accuracy usually satisfies that requirement. It is. If you have infrastructure, so the question here is that it's challenging because even with DGPS, differential GPS, you cannot achieve that. If you have an infrastructure, that means you have base stations, like reference stations that send you corrections through a communication channel, you can do real-time kinematic positioning, RTK, and theoretically that can give you 2 to 5 centimeters accuracy. The problem is the infrastructure. That's very hard to realize in a large scale. Cars are everywhere, every country in the world.
Please.
So the second question you have mentioned, you use the three inputs like resource. First is the optical camera, like taking the images. Second is a LiDAR. Third is the radar. So I'm curious how those, especially how the inputs from LiDAR and the radar can assist to each other.
So, Max, I think it's easier if I just repeat the question instead of moving the microphone. Is, or you can come here. Yep. So the question was how LiDAR and radar complement each other and they are different. Yeah. So LiDAR is more accurate because you send these laser light and you can measure distance with very high precision, like millimeter level precision. Whereas radar is, you don't send laser beams, you send like a long wavelength light, and it's less accurate. But so there's people who think LiDAR is, gives better results, but LiDAR is very expensive as well, whereas radar is cheaper. So I think both of them are useful. Radar is useful for detecting, obstacles or a vehicle that's in front of you, and it's currently being used for adaptive cruise control, but it doesn't tell you what that object is, okay? Or it's harder to recognize objects in radar data. Whereas LiDAR is more, especially with the recent LiDAR ones, you get a quite dense point cloud, so you can recognize objects and also accurate distance. But then LiDARs are more expensive. So I think both of them are useful, and especially in the past, 5-10 years, we've seen LiDAR prices are dropping. So we got one a few months ago, around $15,000, but a few years ago that was $100,000. So it's like one order of magnitude cheaper compared to 5 years ago. Did that answer your question? Usually one. So most of the autonomous vehicles I've seen from like Google Waymo, Ford, Baidu, Uber, they put the LiDAR on the top. So there's one LiDAR. And again, I think that the reason is the price. It's costly. Radar maybe, I don't know exactly how many radar, but radar is cheaper. But I know there's one in front of the vehicle that's always there. But I think that they use multiple radar ones, one in the back and maybe on the sides as well. Yes, we see questions in the chat. Okay, maybe we answer one of these. Eduardo is asking, would be all these algorithms done for AV transferable to other machines? Let's say humanoid robot navigation. Yes, in certain circumstances. So for example, if you have an algorithm for localization that uses imagery or LiDAR to localize the platform, that platform can be a vehicle, it can be a robot. You know, it's the same thing. But in different contexts, you will use different algorithms. If you're using, if you want to estimate the position of a vehicle in a road environment, you would probably use LiDAR with a long range, you know, measuring capability. And if you're using a robot in an indoor environment, you would probably use, you know, a low cost depth camera or a flash LiDAR, which is much cheaper. So depth cameras, you can buy one for, you know, $100, and they give you distance within, you know, 5 meters, distance measurements. You can use those for localization. So I think the type of sensors and the type of algorithms that we use for computer vision tasks depend on the context, the application scenarios. But the principles are the same algorithms, the same methods are used. Should we go to other questions in the chat? Yes, so Gavin is asking, okay, listening from Canada. I don't know what time it is in Canada now, but it's probably too early.
9 o'clock, almost 10 o'clock, Professor.
All right. Well, thank you for joining, Gavin.
Yes.
The question, or maybe you can just say your question instead of me reading it.
I've been given the microphone, so if you might indulge me.
Sure.
My question is about adversarial attacks. What do you think, if someone wished to do harm to an autonomous vehicle ecosystem, what do you think are our greatest vulnerabilities, and how can we start mitigating against them now?
Can I add something? Yes, Max wants to add something.
Just to add something to the same question in relation to false positives, because okay, one purpose of machine learning is to avoid false negatives, of course, but also the false positives. So for example, we know that a few years ago, the MIT students, they trained, they created like some images, like a turtle that was recognized as a rifle, no? And then with some work, it's possible to fool the artificial intelligence system into recognizing this false positive. Is there a way to prevent that systematically? I mean, and in advance?
I think that's a very relevant question, and I think it's certainly possible. Yes, you can hack the machine learning model, you can fool it. Yes, that's possible. But to avoid this issue, I think it falls in the domain of, you know, cybersecurity and how to make these systems safe and secure. And I'm not really, my knowledge of cybersecurity is very limited. So I don't know if it can be 100% avoided or not. I think hacks are always possible. But basically, yeah, so you train a machine learning model to do a certain task for you. And if people use wrong examples, it can be fooled. You know, it can give you false positives. or it can be hacked to, not function properly. Yep. Did that answer your question, Gavin?
Thank you. I mean, Mike, I come from the realm of politics, Professor. So I feel that this is as well as a cybersecurity question, it's also a question about politics and trust. And because we need to think about how societies can trust these systems, and we have to think about how we live in a world of increasing misinformation and disinformation strategies. So for me, it has to move into that area in order to be validly addressed.
Sure, I fully agree. I think cybersecurity plays a significant role in autonomous vehicles. That's one of the dimensions. I said there are multiple dimensions in using autonomous vehicles. But I actually think hacking an autonomous vehicle or basically developing a mechanism to avoid this situation is just like email scams. What do we do for those? We just try to develop more secure cyber systems, online systems, and that's something that should be done for autonomous vehicles as well.
Great. So there's one more question for Professor Michael Regan. Thank you for an excellent presentation. Around 65% of crashes are attributable to driver inattention. For example, distraction, misprioritized attention, paying insufficient attention. How capable are current machine algorithms in knowing what activities are critical for safe driving? The autonomous vehicle must give attention and priority to from moment to moment. So it's how prioritizing attention to different aspects of the visual field.
So I think for the autonomous vehicle, that attention should be continuous. That means the vehicle should watch the road continuously. But again, if we think about the 5 levels of automation, we currently are at level 3, or we're working towards level 3, which means the vehicle can do driving tasks, but the human driver is in charge. The machine learning model basically assists the human driver. That means you're driving the car, but you can take your hands off the wheel, steering wheel, or you can just, in case you don't pay attention to the road, the machine learning model can drive or can warn you. There's also another line of research I've seen using cameras. I think some of the manufacturers also do this. I think Tesla does this, that they have cameras inside the car that looks at the driver and recognizes drowsiness, or if you're not paying attention to the road, and warns you. So yeah, I think that at the moment, this AI model, the role of the AI model is to assist and warn the driver, not to take over the driving. But even for that, it has to watch the road all the time. It should not, it should pay attention all the time. Otherwise, what's the point of, having the autonomous system? Did that answer your question, Michael?
Mike said, thank you. So I suppose, yes. More questions from people in the room?
Thanks for your nice presentation. It was very informative. I would like to know more about the assessment of incidents, things, how you are applying decision making, or what types of decision making is actually working now.
I think for decision making, the first step is to have the right information. And the purpose of road incident detection using sensors is to have that information, to collect that information. And then in addition to that machine learning model that collects the information and recognizes that there is an incident on the road, you need another expert system, if you like, to be able to make an informed decision using this information and deal with that complex situation. So like the example, the sheep on the side of the road and there's a fence, I think that's quite complex. And it's probably a separate machine learning or a separate expert system that should do the decision making, not only for these incidents, but also for other situations. One of the PhD students in our group working with another professor, she was looking at negotiation between the vehicle, autonomous vehicle and pedestrians. And I think that's another situation where you need complex decision making by the vehicle. Actually, it's interesting. My first reaction when they told me about their research was that, what negotiation? You don't negotiate. If the vehicle sees pedestrians crossing the road, they stop. But then there are situations, and that's what they explained to me, that the pedestrian is not crossing the road, but you need to assess their intention. Are they planning to cross the road? And what if they're just standing there forever? Do you also stop forever? I mean, the autonomous vehicle should make that decision. And it's not simple, it's not straightforward, it's quite complex. And it's outside my knowledge, really. I think that the decision-making system is another challenge on its own merit. It's another research domain. I think if yes, yeah. And that's, so the comment here was that if the kid runs in the street, they should make the decision in a split second, and that's correct. But that's one of the things that the AI, the machine learning, can do better than human. It's quicker, it's faster. If you use the right hardware and software, of course. But in principle, computer can be faster than human. I agree, it is, yes.
Thank you. Thank you for your talk. It's very interesting. I have a question which is not really related to technical aspect, but is from, say, what we are talking about is all about algorithms, how algorithm can understand world. But on the other side, we have the whole world. Like nowadays we have concept of smart city, smart road, maybe. Except for the stations you mentioned before that can help readjust, relocate vehicles, what other type of facilities or infrastructure we have, or in the future we have, that can help machine or help autonomous vehicles to be more popular on the road?
Thank you. That's a very good point. What comes to my mind immediately is the connected transport infrastructure. I think it would be very useful. The current vehicles, they have communication devices. It's called the DSRC, dedicated short-range communication, which can send and receive signals within a short range, I think 300 meters or so. I think expanding this communication, so connected transport is a domain of research in transport. And the idea is that all the vehicles, they have the communication devices that they can talk to each other. but also the infrastructure. And that includes the road, traffic signs, traffic lights, anything that's around, for example, intersections. So then they can send information to vehicles and receive information from vehicles. I think that would be very helpful. It helps solve a lot of those challenges I mentioned earlier. For example, vehicle localization. If you receive signals from, points that, their position, they work like beacons, you know that the position of that beacon, and it sends you a signal. You can actually localize yourself with respect to that beacon. And if you know the position of the beacon in your map or in the road environment, then you can localize the vehicle. But there are lots of other advantages of that connected transport. So, for example, in intersections, if you have cameras overlooking an intersection or other sensors that can detect unsafe situations and warn the vehicles, the incoming vehicles, that would help, improve the safety, especially for, vulnerable road users, pedestrians, bicycles, motorcycles, because usually they don't have the sensors that you would put on a vehicle. They don't usually have the, communication, maybe, okay, you can send signals in some way, but they are vulnerable, you don't have the vehicle around you to protect you, and you don't have all those fancy sensors on board the vehicle. So sending information either to those vulnerable road users or sending information about the vulnerable road users to vehicles to, be aware of the vulnerable road users. I think that's one aspect that is very promising. And I know in transport, there's a lot of research on connected vehicles, connected transport, vehicle-to-vehicle communication, vehicle-to-infrastructure communication. In Melbourne, one of my colleagues they founded a big test bed around the university campus. They call it AIMS. You might have heard of AIMS. It's essentially a network of streets with lots of infrastructure, sensors, Wi-Fi routers and communication devices to test the connected transport and use it basically for research.
Interesting when like the training, for example, training of one car, an algorithm on suppose Europe, the road, how does the road look like? And then you have to retrain it on American or Australia. But if like we have localized this kind of camera, it knows the local road, right? And then you don't have to train the car, retrain the car in the new environment because you can communicate with that whatever there. So that you don't have to do the retraining. Yeah.
That's a good solution. I guess it's more of a question of how practical this is, because then, for example, the car manufacturers like, BMW has to open a branch in every country and every city and train models, machine learning models for that particular city or country. I think this is quite challenging in practice and maybe expensive, whereas just making the algorithms more intelligent, that's probably cheaper and might work just as well, But there is a lot of research that should go into making those machine learning models more intelligent. I think if we look at the human, it's similar, similar situation. If you drive in Europe and come to Australia, the first time I came to Australia in 2015, when I wanted to turn right in the intersection, the light was green, so I turned. And then all the vehicles were honking at me because you have to stop until all the incoming vehicles go, and then you can turn right. So it's green for you to turn, and it's green for the other vehicles that are coming. But in Europe, it's never like that. And it was completely new for me. So it's, I think, incremental learning, because now I don't make that mistake. And probably a single shot learning, because it happened only once. So these things, the computer can learn as well. Why not? Yes.
Well, thank you very much for the great presentation. It was very informative and insightful. My question is mainly around the challenges, some of the challenges you listed in the last slide. And apologies in advance if the question is irrelevant, because my research around AI is mainly focused on consumer behavior. So I'm not an expert in AI or machine learning at all. Now, a few of the challenges that you mentioned, I completely understand how that can be a challenge for AI or machine learning in particular, but I don't understand why this is a critical challenge for the operation of autonomous vehicles. Now, let me clarify my question with a few examples. You mentioned incident detection or object recognition as two of the main challenges, and I understand AI algorithms would have difficulties identifying objects that have not been trained based on. But from a vehicle operation perspective, how important or critical that is? I mean, as long as the machine, the vehicle would understand that there is a species crossing the road and understanding that this is a hazard and the vehicle must come to a stop to avoid a collision, that should be sufficient to avoid that collision. Doesn't really matter if that species is correctly categorized as a kangaroo or incorrectly categorized as a cat. So I understand the challenge for machine learning. The part that I have difficulties understanding is how critical that is for vehicle operation. Thank you.
That's a very good point. And the one example that I remember is, I think it was Google Waymo car that they did a test that they put, cardboard boxes on the road. And, if there's a small cardboard box on the road, you wouldn't really brake suddenly, but the machine learning model, they just classified that as an obstacle and, braked immediately, braked hard. I think in most cases, it influences your decision if you know the identity of the object that's on the road. I think it's important. For example, if there is a pothole, you might just swerve around it or just go over it. But if you think that that's a risk to you, you might just stop. And I think that's important for the AI model to know the identity of the obstacle and what type of risk that poses to the driver. But it's an interesting aspect. I don't know what others think. If anyone wants to comment on that?
Classification. Currently, we have classification like when always classify exactly the identity of the object, like either it's cat or it's dog, right? But for car, if it drives, it doesn't matter whether it's car, whether it's dog or cat, as long as it's something you shouldn't roll over it. That would be enough.
So yes, that's good. I just thought of another example that the sheeps, if they were kangaroos on the other side of the fence, they might jump over the fence, right? Because they can jump quite high, but sheep cannot. So it's, I think, just like the way human driver makes the distinction that different animals have different jumping capabilities. I think for the AI AI model is also important to, because you can, attribute different abilities to the identity of that object.
Thanks for the excellent presentation. I have a question about one of the projects you mentioned you are doing at University of Melbourne. You showed an image of a fused LiDAR data and GPS data. Wanted to ask, how do you do that? Is it just, do you map the point cloud, each point to GPS point, or just a midpoint that was recorded, the cloud point cloud to just to one GPS point?
Okay, so there is this is actually a series of works that one of our PhD students is doing. But if you use GPS and you want to do accurate positioning, you use RTK, real-time kinematic. The way it works is that you set up a base station, and that base station it has known position. It receives satellite signals and then communicates the satellite signals to the rover, which is the vehicle.
We use RTK.
Yeah. Okay, so you're familiar. Yeah. Okay, so what we do is, if you don't have that base station, you can use LiDAR to give you to basically serve as those corrections that you receive from the base station, because your LiDAR would give you accurate positioning, but it's not available all the time because the environment might have changed compared to the map that you have. But then when you combine it with the GPS, then when you have LiDAR, it's accurate. When you don't have LiDAR, you use GPS. And because you start from an accurate position and just use GPS signals, you continue your accurate positioning. So the way we did it is by matching the LiDAR scans with a HD map of the environment, which was an existing point cloud of the environment captured at a different time, for example. And it's not only one point, it's basically a deep learning model that finds similar points between your current scan and the map, and then matches these points. So if you find those matches, then your LiDAR positioning is successful and you use it. If you don't find those matches, you use the GPS. So there's basically a Kalman filter that takes these two inputs from the GPS and from LiDAR positioning and integrates them. If one source is not available, the other source is used. And if both of them are available, you basically do very accurate positioning. No, we used the Coyote dataset. I know why you're asking this. This is a good question, because if you want to really do a realistic experiment and test, you need very accurate ground truth for the position of the vehicle, and you need LiDAR data captured in different times, because you want to show that the road environment is different. And this data is not available, and we had problem. So what we did was we simulated accurate positioning. Basically, we have a base station on top of our building in Melbourne, and it's a reference like a base station. You get signals, you know, the exact position. So use that, but then you simulate a trajectory, which we use, for example, from Coyote. So you take the Coyote dataset, because every scan has a georeferencing transformation. You apply that transformation to your GPS positions, and then it's like you simulate the GPS, accurate GPS on board the vehicle. And for LiDAR data, there are a few data sets that include multiple passes of LiDAR data in the same environment, but none of them is perfect. And this is what we're working on to create our own data set, because in reality, the data that you capture and the map, there's no guarantee that they will be exactly the same. The road environment is changing all the time. And the data that we currently have, for example, Coyote, you know, the map and the rover scans of the same data set captured at the same time, same day, you know, it's very similar. So it's obviously not suitable for experimenting. So we simulated the availability by just, you know, simulating failures. We said, okay, what if this scan fails and then the next scan is successful? So when you run this LiDAR-based registration on Coyote, it's actually successful 100%. for all the scans, because it's the rover scan and the map is exactly the same. Very minor differences. But then you can you say, okay, I take one LiDAR positioning solution every 10 frames or every 20 frames or every 50 frames. So that way you can simulate positioning failure of LiDAR. Yeah. Did that answer the question? Other questions?
Thanks. I've actually got a few questions, but the first one is, do the companies very often share code or collaborate with academia? Because obviously there's tremendous competition between people making autonomous cars. So are a lot of them very opaque in how they do things, like Tesla, for example, or do they talk to people?
And that's the problem, because maybe Google Waymo has a nice data set. They've published a large data set, and they've shared basically the AI models, machine learning models, pre-trained models. And they publish a lot of their research. But you're right, basically companies are very protective of their developments. And it's a problem. If they want to develop something, their own research unit develops something, if they want to work with university, they ask the academics to come to their company and work for them instead of collaborating. And I think that's a problem. Baidu, for example, they've developed a nice LiDAR localization method. We tried to use the data set to compare our method with theirs, but it was not possible to. They said we don't share our data. It's just protective. I know Tesla is also hard to get into. They don't share any of their data or models. Google and other companies, they are very sensitive to privacy issues. So if there's no privacy, sometimes they share. Yeah, but it's an issue. It's an issue. Yeah, less than ideal.
What's a vector map?
A vector map. The question is a vector map. So most of the companies that are working on HD maps, I can actually show you. I didn't want this presentation to be too long, so I omitted some of the slides, but I have it here. So this is most of the companies, the car manufacturers that work on high definition maps, they prefer this format where basically all the map features are represented as vectors instead of 3D points, for example, lines, line segments. So the road boundaries, traffic signs, traffic lights, all the other, yeah, that would be good. Thank you. So this is called vector maps, basically line segments. But the problem is you cannot make this generate these maps automatically. So what these companies like Here Map, for example, they do, or I think TomTom, they collect data, usually LiDAR data and imagery, and they have semi-automatic pipelines, but there's a lot of manual annotation to create these maps. Another problem with this representation is updating these. The advantage is that they are very lightweight. So you can have a map of a whole city, and it's like maybe a few megabytes. So it's easy to download the map, and use it in the vehicle. But the problem is generating and updating these. And we're talking about a global scale. So Here Map, for example, they have a fleet of 500 something vehicles. And if they want to, create a HD map of Melbourne, it probably takes them a month. But imagine that you have how many cities that you want to map. So next time they want to update the map of Melbourne, it's probably 5 years later, you know. So that's the map, the update frequency, which is long, let alone all the complexity of manual annotation and manual generation of the maps. Which is why I think this voxel-based representation is a much better solution, because you can make this automatic. You know, in SLAM, we use the occupancy grid mapping, and it can be done automatically, and it can update automatically. I think the challenge here is to do this in a crowdsourced way. And I know some companies, they've already started collecting the data. So I know, for example, Volvo, they collect data from all their vehicles into basically a central cloud, and they communicate it to their own vehicles. So sometimes the vehicle receives information that 2 kilometers in front of you, there's something happening in real time, which is quite interesting. So they can do the same thing with all the visual data from the camera and the LiDAR. And if you have all this data and feed these to an occupancy grid generation, then you can create those voxel maps automatically. And if you keep doing this, you know, collecting data, you can update the map continuously. The problem is the size, because it's a voxel map and the size is huge. And you want to put this on some platform where every vehicle only downloads the part that's relevant, you know, maybe 1 kilometer around you. But even that part is large, and then downloading, and this takes time. So that's an issue. So that's what I meant when I said they use semi-automatic pipelines. They do semantic segmentation, you know, classification, but in the end, there's a lot of manual editing to create those vector maps. So there is currently no automatic pipeline that they can create these maps efficiently. And there's only, I've seen TomTom, you know, TomTom is a navigation company in the Netherlands. It's the only company I've seen that they looked at voxel maps, but in a completely different, it's not a 3D voxel map, it's only like a 2D voxel map across the road. It's called Road DNA, I think. And in research, the maps that I've seen people use for research, everybody assumes the point clouds can be used as the map. But point clouds are obviously too large. You know, every scan is like 30,000 points, and you capture 20 scans per second. Imagine how much storage you would need for the whole Melbourne. Yeah. So that's an open challenge, the HD map generation and updating. There's no solution for it at the moment.
So it was a very nice discussion, and I think the people in the room, well, if you want to stay with us for a little bit longer, maybe we can continue our conversation. But the people who are attending online, well, I'm afraid that we'll have to conclude our connection soon. But first, I would like to read one comment from one of the people attending remotely, because it's very, very interesting and also philosophical kind of consideration about the nature of artificial intelligence. Dr. Murat Tatali says, my comment is that the only way an AI can have or learn the insight that the human has, it should be more than compartmentalized AI components doing great detections and measurements, but should have a somewhat life experience. This could be achieved either by training the AI in the real world or in a simulated world as growing entity that learns to survive while also being ethical. I think that this is the jackpot problem to be solved. And this is a huge question, and I guess we're not going to solve it today, but I don't know if you want to.
No, I agree. I think I fully agree. And as I said, this AI model should be able to incrementally and continuously learn without forgetting that the previous experiences. So yes, I agree, but it's a challenge also for autonomous vehicles.
Great. We thank again Professor Kourosh Khoshelham for being with us and for giving this great presentation that was not only very interesting, but also extremely clear. I thank Matthew Garrett for being with us and all the people who have attended this seminar online or remotely. And I want to remember that the next seminar in this series is going to be in 3 weeks time. And so please keep in touch and I will share all the details. And thank you very much and see you soon.